So in this video we should be able to wrap up the last two pieces of the problem number 5 from the 2008 Form B of the AB Calculus exam. And what I did to kind of start things off here was I stole some work that we had done in Part B in the previous video. And we determined in Part B that g of negative 3 is 15 halves, and we determined also that g of 7 is positive 3 halves. What we're asked to do in Part C is we're asked to find the average rate of change of g on the interval from negative 3 to 7. Well, the average rate of change of a function is simply going to be the slope of the secant line connecting the endpoints of the interval. So all we're going to need to do here to find what the average rate of change of g is on the interval negative 3 to 7 is apply a regular old slope formula. It's not an instantaneous rate of change. It's not the change at an instant. It's not the slope of a tangent line. It's an average rate of change. So over the course of this piece of the x-axis, the average rate of change is going to be given by the difference between the y values there. So that's going to be 3 halves minus 15 halves. I'm just taking those answers, the y values, the function values that we determined in Part B, and then I'm going to divide by the corresponding difference in x values. So that's going to be 7 minus negative 3. And if you go ahead and simplify this, you should be looking at negative 12 halves in the top, and in the bottom you're looking at positive 10. So in the top, if you go ahead and simplify that fraction, you're looking at negative 6 over 10, or an average rate of change of negative 3/5. So the average rate of change of g over the course of the interval from negative 3 to 7 is going to be negative 3/5. And then in Part D, it says find the average rate of change of g prime on the interval negative 3 to 7. So the average rate of change of g prime on this interval is going to be g prime of 7 minus g prime of negative 3 divided by 7 minus negative 3. So it's the same regular old slope formula, but not applied to g, applied to the graph of g prime. So we can steal these numbers right off of the graph. G prime of 7 is 1, they give that to us, minus g prime of negative 3. So g prime of negative 3 is negative 4, they give that to us on the graph as well. And then 7 minus negative 3 is 10 in the bottom, so we're looking at positive 5 over 10, or 1/2 for the average rate of change of g prime on this interval. Does the mean value theorem applied to g prime on the interval negative 3 to 7 guarantee the existence of a c such that g double prime is equal to this average rate of change? Why or why not? So in order to use the mean value theorem, two things had to be happening with the function you were applying it to. And in this case, we're applying the mean value theorem to g prime of x. G prime, or the function you're applying the mean value theorem to, has to be continuous on the interval you're considering. This derivative, g prime, is continuous on the interval negative 3 to 7. We don't see any holes or asymptotes in the graph that we're provided with, so we know that our function is continuous. But the other condition that has to be met in order to use the mean value theorem is your function has to be differentiable on the interval that you're considering applying it on. This function is not differentiable as x goes from negative 3 to 7. We know it's not differentiable because we have cusps at negative 1, at 1, and at 4. So there are really 3 points in between negative 3 and 7 where g prime is not differentiable. 3 points where g double prime does not exist between negative 3 and 7. So does the mean value theorem guarantee the existence of a c? No. The reason why is because g prime is not differentiable on this interval. So if you think about it, the slope of this line segment right here would be, let's see, to get from this point to this point, we'd have to do a rise of 1, 2, 3, 4 over a run of 2. So the slope of this line segment would be 2. So the value of g double prime is 2 on this interval, and the slope of this line segment would be, let's see, a rise of 1 and a run of 1, 2. And so we have a rise of 1 and a run of 2 here, so the slope of this line segment is 1/2, and hence g double prime is equal to 1/2 on this interval. But there's no guarantee that that had to happen because of the mean value theorem. Coincidentally here it worked out that way, but the slope of this line segment very well could have been 1/3, and we go from the slope of 2, we cross the slope of 1/2 whenever we drop to the slope of 1/3 without gradually crossing all slopes in between. So that's why this isn't guaranteed by the mean value theorem value of g double prime being equal to 1/2, but in this case it did happen.